In this section, we're going to be looking at solving systems of equations that have three variables. We know that if we have a single equation with a single variable, then we can solve by eliminating the variable. If we have two variables, then to solve, we need to have two different equations. The number of equations has to match the number of unknowns that we have. We use this process of elimination where what we try to do is remove one of the existing variables so that we can convert it back into the scenario that we had here with a single variable and a single equation. Let's suppose that we decide to eliminate the x variable in this case. What we would do is multiply the first equation by a number and the second equation by a number so that when we add the two equations together or combine them, the x variable goes away. The least common multiple between the coefficients on x is 20. So I'm going to multiply that first equation, let's say by 5, and I'm going to multiply that second equation by a -4. I'm choosing those numbers so that the x coefficient ends up with 20, a positive 20 and a negative 20, so that they will eliminate one another. So this equation changes into 20x plus 10y equals 40. And the second equation changes into negative 20x minus 12y equals a negative 36. Now I combine these two equations together. I'm going to add each of the columns to get a negative 2y equals 4. So y is equal to negative 2. Now I do what's called back substitution. I take this variable that I found a value for and I go back and substitute it into one of the original equations. Let's just put it into that first equation that we had. I'm going to substitute y equals negative 2 in there. So we'll have 4x plus, well, I guess 2 times negative 2 will be minus 4. So 4x is equal to 12, and we're getting that x is equal to 3. So the solution to this set of equations that we started with is 3, negative 2, and I could check my solution by plugging back into the both equations originally just to verify that they make both equations true. We're going to extend this idea to systems of three equations where we have three variables and come up with a number of ways to solve these. And then we'll look at a couple applications. Because we have a system of three equations shown here in this slide, we know that the solution is going to be of the form of an ordered triple, with the first coordinate corresponding to x, the second corresponding to y, and the third corresponding to z. If we want to verify that this is in fact a solution to this system of equations, this is the system here, we'll just plug each of those variables in to just check each equation. And so I'm going to substitute 2 in for x, and negative 1 in for y, and 0 in for z. And we want to know what that equals. Well, 8 minus 2 plus 0. Yeah, we're getting 6 here, so this one works out. For the second one, we would have 4 plus 1 plus 0. Yeah, that equals 5, right? And for the third, 6 minus 2 minus 0 gives us 4. So we can see that that is the single solution that makes each of these three equations true. The process that we use is similar to what we were just looking at for two equations. It's called Gaussian elimination. We have the opportunity to exchange any two equations, multiply an equation by some non-zero constant. We multiplied by a 4 and a negative 5 before. And then also add two equations together. So these are sort of the three rules or ways to change the equations that are allowed that don't change the original value. If I interchange two equations, I'm just moving the order. I might want to reorder them to make elimination of a variable more convenient. When I multiply both sides by a constant, what I'm doing when you multiply by a scalar of a line, all you're doing is stretching the line to be longer. So you're not moving where its x or y intercepts are, you're just making it lengthier, which is sort of an interesting concept because we know that a line goes on infinitely in both directions. So to say that you're making it longer, it's still just going to infinity in both directions, but not changing any of the values. And then when we add two of them together, again, our purpose is to combine them in a way that one of the variables gets removed. The goal is to end up with this triangular pattern where your third equation has only one variable. Your second equation has two, so then you could take z and plug it back into this first one to figure out what y is. And then once you figure out y and z, you'd plug them back into the first to find x. And that's called back substitution. I'll show an example of how to do this. So here's an example. And just for convenience, each of the three equations is labeled. It's just the first one, the second one, and the third one, so that we can keep track of what we're doing in each of the steps. So the first thing that I want to do is try to get this down to two equations with two variables, because we know how to solve that. So I'm going to pair up two equations at the same time to eliminate one variable completely. I'm going to, in this case, eliminate the x's. And so I'm going to start by combining equations 1 and 2 together. So I'm going to take, I want to think about getting rid of x, so I want a negative 4 in front of the x in that first equation so that I can add them together, get rid of the x. So I'm going to take equation 1 and I'm going to multiply it by a negative 4. And that gives me negative 4x plus 8y minus 12z equals a negative 44. So each of the terms has been multiplied by negative 4. And then I'm going to add that to equation number 2. So I'm just going to write equation 2 as it is. And then combine these two equations together. I can see that the x's will go away. I've got 10y minus 15z equals a negative 40. And let's call this equation number 4. I'm going to repeat this process with equations 1 and 3 now. I'm going to follow this same idea for equation 1 and equation 3. Again, I'm trying to eliminate the same variable, the x. So I want to get a negative 3 in front of that first coefficient, or in front of that first equation, so that I can add them together and get rid of the x. So I'm going to do, this time, equation 1 multiplied by a negative 3. And then I'm just going to add that to equation 3. So I'll write equation 3 as it is. Combine these two together. And we get 9y minus 10z equals a negative 29. And let's call this equation 5. Now I'm going to take equation 4 and 5, and I'm going to try to eliminate one of the variables. I've gotten this down to two equations with two variables, and I'm going to solve this the way that I was at the very beginning of this video. So I'm going to eliminate the variable y. So the least common multiple between the 9 and the 10 is going to be 90. Let's multiply that first equation by a negative 9. So we'll do equation 4 multiplied by a negative 9. Negative 90y plus 135 z. Let me just check that. 9 times 15. Yeah. Equals 360. Okay. For equation number 5, we're going to multiply that one by 10. So 90y minus 100z equals negative 290. Okay, let's add these together. I can see that the y is going to go away. So it looks like we've got 35z equals 70. So z is equal to 2. Good, we found one of the variables. And now we'll go through a process of back substitution. I want to go back to one of the two variables that has, one of the two equations that has only two variables to plug that z in. So let's go back to equation 4. Plug z equals 2 into equation 4. Equation 4 was 10y minus 15z, but instead of z, we're going to put a 2 there, equals negative 40. Let me just double check. Yeah. Okay. So 10y is equal to a negative 10, so y is equal to negative 1. And then we'll go back to one of the equations that had a single variable. Let's go back to equation 1. Let's plug y equals negative 1 and z equals 2 into equation 1. Equation 1 was x minus 2 times y plus 3 times z equals 11. Let me just double check. Minus 2 plus 3. Yeah. So we have x equals, let's see, that'll be 11 minus 2 and minus 6. 3. X equals 3. So our total solution to this system of equations is 3 for x, negative 1 for y, and 2 for z. We could go back to that original set of equations and plug that single point in to make sure that it made all three of these equations true. This slide here is showing us what the possibilities are for solving a system of 3 equations. Just did falls into this first category where we get a single solution. And you can think of this as like the x, the y, and the z plane intersecting in a single point. The x, y, z plane, the point that they intersect in is the origin. But the equation or the solution that we just came would be the point of intersection of those 3 planes. We could also have the 3 planes sort of in this triangular format where there's not a single solution because if I take 2 individual equations, they intersect one another in a line, right? So I've got this line here where these 2 intersect, which is different from, say, this line of intersection. The third example shows no solution at all, where all 3 equations are parallel, meaning that they're multiples of one another. We could have infinitely many solutions where the equation ends up being a line. It's not a single point, but we actually get a line as a possibility. And then this could be this last example. All of them are exactly the same. They end up being the same plane, just in a different format. So let's look at an application example. Luis inherited $15,000 into 3 different types of accounts: a money market, a municipal bonds, and a mutual fund. After a year, he had earned $730 in interest, and each of the investments paid a different percentage in return. We're trying to figure out how much money he invested in each category. So let's start by assigning variables to each of the categories. The first one was a money market. Let's let the variable X be for the money market. And let's let the variable Y be for the bonds. And then Z will be for the mutual fund. The money market earned 4%. The bonds were 5%, and the mutual funds were 6%. Okay. So if X is the total amount of money that was earned for money markets, and Y for bonds, and Z for mutual funds, we know that the total he invested was $15,000. So X plus Y plus Z equals $15,000. We're just X, Y, and Z are the total dollar amounts he invested in each type of account. The interest that he earned is going to be 4%, so 0.04 times the amount that he invested in that account. 5% for the second account, and 6% for the third account, right? This is just 6% of the total invested. And all of those 3 interests earned total up to $730. And then the last part says that there were $2,000 more invested into the mutual fund than in the bonds. So however much he invested into bonds, if we add 2,000 to that, that would be how much he invested in the mutual funds. So this would be rearranging this. Negative Y plus Z equals 2,000. I just subtracted Y from both sides here. So now I've got my 3 equations and my 3 variables. The nice thing is that that third equation, let's call these equations 1, 2, and 3. The third equation already has only 2 variables. So we want to take equations 1 and 2, combine them together so that we can get rid of, in this case, X. Because if we get rid of X, then we can combine it with that third equation there. I'm going to take equation 2 and multiply everything by 100 just to get rid of those decimals. So let's do equation 2 multiplied by 100. That'll give us 4x plus 5y plus 6z equals 730, and add 2 zeros. Okay. And then I'll take equation 1 and multiply it by a negative 4, yeah, so that I can get rid of the x variable. And this will be negative 60,000. Yeah. Okay. Add this together. What do we get? We get a y plus z equals, oh, wait a minute. That should be a 4. Back up. I don't know why I wrote a 5 there. Okay. That should be a 4. So this should be a 2z 13,000. Okay, let me just double check. So the first equation, we multiplied by 100. It was equation 2. Equation 1, we multiplied everything by -4, and then I added these two together. Okay, good. And now I'm going to call this, let's call this equation 4. And we want to combine it with equation 3, which was -y plus z equals 2,000. All right, we're going to combine these two together. So I've got 3z equals 15,000. So z is $5,000. Okay, that's good. Now we'll go back to one of the two equations that has only two variables. Let's just go back to equation 3 right above here. So let's plug in z equals 5,000 to equation 3. So negative y is negative 3,000, or y is equal to 3,000. And then we'll go back to one of the first equations. Let's just go back to equation 1. That's the easiest. So now we'll plug in y equals 3,000 and z equals 5,000 to equation 1. So we had x plus y plus z equals 15,000. And we get that x is 7,000. So our solution is 7,000, 3,000, 5,000. And that's the amount that was invested in each account. Next, we're going to look at a common application, which is called curve fitting, where we try to come up with a model, a quadratic in this case, based on a given set of data points. The reason that a quadratic falls into this category is because the variables, or the unknowns, are a, b, and c, the coefficients or the constant. We don't know what those values are. If we're going to find the equation of a line, we know that we need to have 2 points that we can use to find, let's say, the slope, and then eventually the y-intercept to get us to, y equals mx plus b. But when we want to find a quadratic, because there are 3 unknown quantities, coefficients a, b, and c, we need to have 3 data points. We're not talking about x in any of these cases because x is the variable, right? X is the variable. We're talking about the, the numbers that make up the particular equation. So in this example below, we have total number of airline passengers. These are in millions. For 3 particular years, 2008, 2010, and 2012. We're going to consider 2008 to be sort of the starting of this model that we're building. And so in that year, we're just going to scale it back to say, okay, that'll be 0 years after the year 2008. So our variable x is going to be the number of years after 2008. So then that would make sense that for 2012, x is going to be equal to 4 years later. And then f of x, or y, is going to be the number of passengers in millions. So we've got 3 data points here. They are 0, 743, 2, 721, and 4, 737. Okay. And we're trying to find a quadratic equation, ax squared plus bx plus c, which models this data so that we can use it to predict into the future how many passengers we think we'll have. I'm going to use this quadratic equation and plug in the variable for x. So I have a times 0 squared, b times 0 plus c, or c, this equals the y value, 743, right? So I'm getting, in this case, I'm getting that c is 743. That's pretty easy, and that makes sense because that's our baseline data, right? It's our starting point. For the second equation, we have a multiplied by x squared, or 2 squared, b multiplied by x, and plus c equals 721. And for our third equation, we have a multiplied by x squared, b times x, plus c equals 737. Let's rearrange these equations. So we've got 4a squared plus 2b plus c equals 721. Hang on a second. Here we go. 721. And then the third equation is 16a squared plus 4b plus c equals 737. Well, the nice thing is that we've already got c equals 743, so I can plug that into equation number 2 and equation number 3 to kind of simplify them, right? So equation 2 is going to change. Hang on a second. I just had to fix my slides here. Okay, so we're going to take equation number 2, and it's 4a squared plus 2b. We know that c is 743, and that equals 721, or 4a squared plus 2b equals, subtract that 743 from both sides, and I'm going to get a negative 22. Yeah. And then for equation 3, we have 16a squared plus 4b plus that 743 equals 737, or 16a squared plus 4b equals 737 minus 743, negative 6. So I'm going to take this equation and this equation and solve them simultaneously. Oops. These should not be, timeout. Let me back up for a second. I wrote a squared here, and I didn't mean a squared, I meant a. I wrote squared because the variable is squared there. The variable was 2, which squared to 4. The variable in the second one was 4, which squared to 16. Similarly here, we shouldn't have squares on any of these. These should all just be a. All right, we're trying to find a and b. We have two equations with two variables, so we're going to combine them together. I'm going to multiply this equation by a negative 4. So I'll have negative 16a minus 8b equals 88. And then I'll leave this equation just as it is. 16a plus 4b equals negative 6, so that we can add them together, eliminate the a. So I've got negative 4b equals 82. Let me divide here. So we get negative 20.5. Okay. So then I will go back to, let's say, this equation here. Plug in that negative 20.5. So 4a plus 2 times negative 20.5 equals negative 22. So negative 22, it's going to be plus 41, is 19. So A is 4.75. All right, again, what we're finding are the coefficients in front of each of the terms. The original equation was ax squared plus bx plus c. We found a to be 4.75. B was negative 20.5. And C from the beginning was 743. And this is our equation that we can use to model and predict the number of passengers in the future. The original problem asked us to predict how many passengers there would have been in the year 2013, which would be 5 years after 2008. So let's do f of 5. So we'll have 4.75 times 25 minus 20.5 times 5 plus 743. Plug that into calculator. And I'm getting 759.25. This is in millions, right? Let's do this for 2020. What would it be for the year 2020? X is going to be equal to 12, right? So let's do f of 12. Four 0.75 times 144, x squared, times 12 plus 743. Let's see. The interesting thing is that we know, based on the pandemic right now, that these numbers are probably not true at all because the number of people traveling has significantly decreased. But it says 1181 million, which would be 1.1 billion, right? All right, that's all for this video. Thanks for watching. I'll see you in class.